this week's first video, and we're gonna be talking about population dynamics. Usually in this course, we take an ODE and we try to build the solution depending on the ODE. This week, we're just gonna try to approach the topic in a slightly different way. We have a vague understanding about how populations should change over time, and we're going to try to find an ODE that has the appropriate solution. So let's first look at one specific type of ODEs. They're called autonomous. If you have the usual ODE format, that is a function of time, y, and all the derivatives of y equals to 0, an autonomous ODE is when the function doesn't depend on time, but only on y and all its derivatives. So for example, if you have something like y prime plus y second plus y to the third equals to y, this is an autonomous ODE. If you have dy dt equals 5y, this is again an autonomous ODE. While if you have something like y prime equals to 5t, well, t actually appears explicitly in the definition of the ODE, so it's not autonomous. Autonomous ODEs can be linear, as these examples. They can be non-linear. They can have a lot of possibilities, but the main element is time does not appear explicitly. Why are they special compared to other ODEs we can look at? Well, in the case of autonomous ODEs, if y is a solution, then y computed at time plus c for any value of c is also a solution. What does that mean? The idea is that you can shift the solution over time, and it's still a solution of the same ODE. Obviously, the initial conditions are changing, but if we're not fixing the initial conditions, a time shift doesn't change the solution. If y is a solution, shifting it over time will retrieve another solution. So for example, if you have y prime equal to y, in a certain sense what you can do is to wait to start the experiment, and the behavior you see will be different. Well, if you have something like y prime equals to t, waiting to start the experiment changes the state of the system, so the behavior of your solution will also be different. Now that we know what autonomous systems are, we can understand how it's interesting to look at autonomous systems when talking about population dynamics, because we expect population to change only depending on itself, not depending on what time it is. So the first approximation, the first modeling of population dynamics we will do is through exponential growth. So we say that the growth of the population, so y in this case is how many individual the population has. We consider y a real number, not integers, but we look at y and we say that the growth of the population, so dy dt, depends on the population itself. So in a certain sense, we're looking at the standard example of rabbits replicating. If there are 2 rabbits, they're going to be like 2 kids. But if there are 4 rabbits, there are going to be 4 kids. So depending on the size of the population, the growth, it's a coefficient times the size of the population. So we say that this coefficient r is the rate of growth, if r is positive, as we expect it to be in our condition, or the rate of decline if it's negative. The solution of this ODE, you can do it by separation of variables, you can do it in other ways as well. It's the exponential. So y over time is equal to y0, that is the starting value of the population, times the exponential of r, that is the rate of growth, times the time. That means that the population grows exponentially fast, and it grows forever. This is, when you look at it from a modeling perspective, unsustainable. You do not expect the population of rabbits to grow exponentially fast for forever, because that would mean that the earth would be covered in rabbits, and we see that that's not the case. So we want to do some more refined modeling to find something more sustainable. So we build up a new model. The base structure is the same, y prime equals something times y, but the something is now not a constant anymore, but a function of y itself. We want something there that first allows for an exponential growth, then it slows the growth down and stops the growth altogether by becoming negative. What would be the simplest example? Well, we want hy to just be a decreasing line. We start at the value r, so for very small populations the growth is exponential, but at some point our h touches 0, so the population doesn't grow anymore. If you're over that, h is negative, so the population is decreasing. The equation we get when we put h inside the model is y prime equals r minus ay times y. We call this the logistic equation, just the name it has. We can rewrite it a little bit as y prime equals r times something times y, with the something being 1 minus y over k. K is in this case r divided by a. Why do we like to write it like this? Because this is just a change with respect to what we already had, and r reappears. We call it here the intrinsic growth rate. The first thing we want to ask when we have ODEs is, are there equilibrium solutions? And we do that by solving the right-hand side as a function of y and setting it equal to 0. So we do find two equilibrium solutions, one at 0 and one at k. So the idea is that fy, that is the derivative of y, is a parabola crossing the 0 axis at 0 and at k, and having a maximum at k over 2. That means that from 0 to k, the first derivative of y is positive, and if you are over k, then the derivative of y is negative. But when you write things like this, you are talking about y as the phase line. If we do the direction field, you see that y equal to 0 is an equilibrium solution, so it's always there as a solution in red. Y equals to k is also a solution. And between 0 and k, your ODE pushes solutions towards k. When you are over k, your solutions decrease towards k. And we're under 0, we don't really care because populations can only be positive. But if you did care, well, then things will be pushed away from 0. So plotting in some solutions, what you see is that solutions that start over k decrease towards k. Solutions that start between k and 0 all have a roughly an S shape towards k, and they all squeeze in towards k. And solutions that start under 0 go away to minus infinity. Is there an inflection point of the solution? What does it mean? Well, when we were looking at solutions that were between 0 and k, we said that they were doing an S. There is a point in which you stop going upwards and you start going more sideways in a certain sense. Where does that inflection point is? Well, the inflection point is where y second is equal to 0. So we compute y second as derivative over time of y prime, that is derivative over time of f computed at y computed at t. So we get f prime times y prime, f prime computed at y and y prime computed at t. But we know that y prime is f, so y second is f prime computed at y times f computed at y. When is y second positive? It's either when f prime is positive and f is positive, or when both of them are negative. While y second is negative when the two elements have different signs. So either f prime is positive and f is negative, or the other way around. The inflection point is where f prime times f is equal to 0. And that happens at k divided by 2. So if you look at the solutions that we built up, what we have is that if your y0, if your starting condition is positive, then it doesn't matter if you start at k, below k, or over k, everything will tend to k over time. What we call k is the carrying capacity. That means that in the environment you're envisioning for your population dynamics, that is how much the environment can sustain of the population. Because of this behavior in which everything in the neighborhood moves towards y equals k when you tend to infinity, you call the solution, yt equals to k, an asymptotically stable solution. On the other hand, y equals to 0 has the opposite property. Everything goes away from it. Maybe not that far away in the sense that some of them goes to k, but they all move away from it. It's called an unstable equilibrium solution.